In section 5.4, we combine finding integrals like we did in 5.1 and 5.2 with finding areas like we did in 5.3. Kind of combine the skills together, but we're not doing any geometry per se. It's mostly just going to be calculus. And this is specifically what we're going to do. We're going to learn something called definite integrals as opposed to indefinite integrals. The symbol that we worked with in sections 5.1 and 5.2 was called an indefinite integral because it could take on many answers. I don't have a definite answer to it because of the plus c. There's lots of different functions that have the derivative of the integrand. Definite integrals have little numbers on the integral signs, and these numbers relate to the rectangles that we did in section 5.3. They're kind of the left edge of the first rectangle and the right edge of the far right rectangle. So this definite integral symbol, this is the symbol that's going to allow us to calculate, I'll say, net areas between the graph of a function and the x-axis, provided the graph doesn't have any breaks in the interval a to b. So this definite integral is just a new notation. When you put numbers, that those a and b are going to be numbers, the indefinite integral turns into a definite integral. And with definite integrals, we can calculate, I'll say, net areas between a graph and the x-axis. It has to do with areas beneath the x-axis having negative areas. So very specifically, this is a big deal. The fundamental theorem of calculus, I wrote it correctly, basically says if I know the integral of some if the indefinite integral simplifies to some function, then I can calculate the area of that function between two values, a and b, if I just take the integral, plug in the far right edge, plug in the far left edge, evaluate those in the integral, and subtract. So the fundamental theorem of calculus allows us to calculate net areas over an interval given a function that doesn't have any breaks in it. And very specifically, in words, the theorem says if you're given an integral that has numbers on it, that's a definite integral, we can use it to calculate net areas. How do we calculate the area? We calculate the area by first performing the integration, then plugging in both b and a into the integral, getting a separate number for each, and subtract, and then we'll get the net area. We'll get the result of the integration, and the result of the integration is a net area. And let me show you what I mean. So we're dealing with this parabola a lot in section 5.3. This is just the graph of f of x equals to x squared, and I have shaded between x equal to 1 and x equal to 5. And in that section, section 5.3, we did estimates of this area using using rectangles. Well, the fundamental theorem of calculus says that if I know how to integrate the function, then I can get this exact area. Essentially what this theorem does, the fundamental theorem of calculus, is it, instead of doing 2 rectangles or 4 rectangles or 3 rectangles, it does infinitely many rectangles. To develop this equation, you need limits at infinity, and it's pretty complicated to even show how the formula is derived. But if I want to calculate this shaded area, that's what a definite integral is going to do. This is going to calculate the area between x equal to 1 and x equal to 5 of the function x squared. And how do I do it? Well, first I find the integral. So it comes in steps. To calculate the area using the fundamental theorem of calculus, first I perform the integration, then I evaluate the integral at the top number and then at the bottom number, and I subtract those results. That will give me the area. If the entire graph is above the x-axis, it's the total area. If the graph is half beneath the axis and above the x-axis, it gives me a net area. And let me show you. So how would I integrate this? Well, that's just a generic power rule. To integrate this function, I'm going to add 1 to the exponent and multiply by 1 over the new exponent. When I have indefinite integrals, I tack on a plus c. But if I was to use the plus c here, it's going to cancel each other out, so it's not necessary to do the c's. So first I'm going to find the integral, just using the general power rule, and then I'm going to emphasize, I'm going to need to evaluate this integral at 1 and at 5. So the first step is just to perform the integration. Second step is to evaluate the integral at the higher number and then the lower number. So let me do that computation. I'm going to evaluate the integral at the higher number, which is 5. So I'm going to plug 5 in for that x and do 1/3 times 5 cubed. That's evaluating the integral at the higher number. So I did 1/3 times 5 cubed. Well, 1/3 is just 1/3. 5 cubed is 125. And I thought of this as 1 over 3 times 125 over 1. And I multiplied the 1 times 125 and got 125. I multiplied the 3 and 1 and got 3. So evaluating the integral at the larger number, I get 125 over 3. And then I'll evaluate the integral at the smaller number, 1. So I'll do 1/3 times 1 cubed. 1 cubed is just 1, and 1/3 times 1 is just 1/3. So I evaluated the integral at the higher number and got 125 over 3. I evaluated the integral at the lower number and got 1 over 3. That's the second step of doing the integration. So I did the integration. I evaluated separately at the higher than the lower number. To get the area, I'm just going to subtract the results. So let me do the subtraction here. I'm going to subtract the number I got from when I plugged 5 in, which is 125 over 3, minus the number I got when I plugged 1 in, which is 1 over 3. Those fractions have the same denominator, so I'm going to leave the over 3 when I do the subtracting. And then 125 minus 1 is 124. And 124 over 3 is the exact area. If I wanted to write an answer on a test, this is the answer I would expect for the answer to this definite integral. If I want to check, I'm going to make this into a decimal, and I'll show you how to check these on your calculator. So this calculator is running dead on batteries right now, and it doesn't show up so well here. But I want it to show both calculators. So if I did 125, you just can't see this calculator. I can't show it. 125 over 3, I need to do on my older calculator. So depends on the lighting. Really struggle with lighting in my little den office room here. It says 41.66. Apparently, well, because I did 124 over 3. That's right. So this area is 41.33 as a decimal, rounded to 2 decimals. 124 over 3 exactly. What if I want to check my work? So easy to check my work, I shouldn't skip checking my work. To find the decimal version, what I'm going to do is go to my y equals and enter the function that I'm integrating, the function x squared. Make sure nothing else is in your y equals. Make sure like you don't have any plots on. So go up to the plot and hit enter to shut it off if you have any plot that's darkened. And clear out all the other functions and just type in x squared into y1. Regardless of how new or old your TI calculator is, this will work fine. And now I'm going to graph it by going zoom and standard. That's nothing new. But getting the area is going to be new. So to get this area, I'm going to hit the second key, followed by the trace calc key. I'm looking for the calc option as opposed to the trace option. So second, trace calc. And then I go down to the integral symbol. So I go down to option 7. Either type the number 7 or scroll down to the number 7 and hit enter. The both will do the same thing. And for some reason my calculator is programmed backwards from reality. My calculator now says lower limit. The lower limit is the number 1. So now I'm just going to type 1 and hit enter. And then after that, it's going to say upper limit. And for the upper limit, I'm going to type 5 and hit enter, and I'm going to be done. On my more expensive calculator, it's actually harder to see the integral answer. It's written there, it gives you a couple numbers, and it's the smaller number up top. But anyways, I'll type in 1 and hit enter, and now I'll type 5 and hit enter, and it gives me this 41.33, and it even shows you the area that it calculated the best it could. My the graph shades off the screen because my parabola doesn't go up high enough, but that's accurate enough. So that's kind of everything that we need in this section. I should give a little more theory before we do some problems. Very specifically, I say that this theorem gives a net area. And what I did is I graphed the function f of x equals x. That's what this line here is, f of x equals to x. And I shaded starting at x equal to -2, ending at x equal to +2. If you see, there are two distinct triangles here, a lower triangle and an upper triangle. And if I know anything about triangles, I might be able to find their areas. This left triangle from here to here is 2, and from here to here is 2. And this is a right angle here. To find the area of this left triangle, it's this 2 times that 2 divided by 2. It's base times height divided by 2. So the left triangle, it's these two lengths, base times height. I don't know which one's the base and which one's the height, divided by 2. It's half the base times the height, or base times height over 2 for the area. And so this triangle has an area of 4 over 2. It has an area of 2 units. The right triangle, similarly, it's 2 that direction and 2 that direction. The area of the right triangle, it's the same base times height over 2 for the area. And these are interchangeable as base times heights because these are right angles. So this is 2 times 2 over 2, which is 4 over 2, which is 2. So each one of these triangles has an area of 2. If I went to integrate, if I integrated this function, the function x dx, from starting at -2, which is the left edge of the first triangle, ending at +2, which is the right edge of the right triangle, it's not going to give me 4. It's not going to go, the total area is 4. This triangle has an area of 2. That triangle has an area of 2. Total area is 4. It considers regions beneath the x-axis as negative areas. It's going to say this left triangle has an area of -2. The right triangle, because it's above the x-axis, has an area of +2. The net area, that's why I call this net area, is going to be 0. So if I do this integral, it's going to come out to be 0. It doesn't actually give me the whole area unless the entire graph is above the x-axis. In section 5.5, we learn how to get around that. If I want this area to be 4, the area of that triangle plus that triangle, I have to calculate the area separately, make this negative area positive, but that's the next section. We don't need to worry about it. So let me show you, by doing this integration, that's exactly what this picture is. So the integral is going to calculate this area plus that area, making that area negative, and let me show you the algebra. So this right here should come out to be 0, because pictorially I can see that the areas net out. How do I do a definite integral? Well, I do the integration first. This is just a general power rule. I'm going to do the integration by adding 1 to the exponent. There's an implied exponent of 1. When I add 1 to the exponent, I get 2. And then I multiply by that fraction 1 over the new exponent, which is going to be 1/2. Don't need the plus c when I'm going to plug numbers in. It really would just cancel out if I put it in, because you're subtracting, and the subtracting would make the c's cancel. Leaving these numbers on my now vertical bar that the integral symbol kind of morphs into. This is the integration. How do I get the net area? Well, after I do the integration, I plug the top number in, get a number for it, plug the bottom number in, get a number for it, then subtract the numbers. So let me do that. Plug the top number in, the top number is 2. When I plug 2 in, I get 1/2 times 2 squared. 2 squared is 4, and I know that half of 4 is 2. So when I plug the top number in, I get 2. I'll do the same thing for the bottom number. 1/2, and then for that x, plug in -2. So 1/2 times -2 squared. The quantity -2 squared is +4, so this also gives me 2. Both of those triangles had an area of 2. But to get the integral, I have to subtract the first computation minus the second computation. So the first computation is 2 minus the second computation is 2. I get 0 for the net area. So what the fundamental theorem of calculus is giving us is the net area. It negates the area beneath the x-axis. Let's do a few more practice problems before we get into the homework. As much as anything, you need to be able to integrate. If you remember your integrations from sections 5.1 and 5.2, and you haven't forgot it after we did section 5.3, then you're golden. If you forgot how to do integration, then you're going to have to go back and relive sections 5.1 and 5.2 to get good at it. So if I wanted to integrate this, because that's the first step in finding a definite integral, if I want to integrate, I need to bring the constant out front using the rule that says if I have a coefficient, I can bring it out front. So I can rewrite that problem with a 6 as its coefficient. And then I have x to the -1. Well, I know that x to the -1 integrates to the natural log of x. So this whole guy right here, it's going to have a coefficient of 6 in the integration. The x to the -1 integrates to the natural log of the absolute value of x. I don't need the plus c, but I need to keep the 1 in the e. So this is doing the integral, just doing really one step, bringing the coefficient out front and then applying the ln rule. Now I need to plug the numbers in. I need to plug the top number in and the bottom number in separately and get each result. I used e's here because I come up a little bit in Math 218, so I want you to be kind of not afraid of e's and maybe do them on a calculator. So what do I get? When I plug the top number in, I do 6 times the natural log of e. That's the first thing I need to do numerically after I integrate. And then I'll plug the bottom number in and do 6 times the natural log of 1. The natural log of e is 1. If I don't know that, my calculator can do it for me. So go back to the main screen. If I want to do this top computation, I go 6. I type the natural log button. And if you look on the divide key, I see a naked e without an exponent. It's written in blue, so if I hit the second key and then the divide key, this is going to tell me what 6 times the natural log of e is. My calculator tells me it's 6 because the natural log of e is equal to 1. So the first computation that I need is 6. The second computation is going to be 0 because the natural log of 1 is 0. But if I don't know that, I can do this just fine. I could go 6 times the natural log of 1, and that gives me 0. So now I've done the two computations. Again, I first perform the integration, then I evaluate the integral at the higher number, then the lower number. The answer, the net area, I just subtract those results. So the area is going to be found by taking that 6 minus that 0, and then I get 6 for my area. Let's check this on our calculator to make sure it's okay. It's a little bit funky, so I think I can do it though. So on my calculator, into the y equals, clear out anything that's in there, and now I go 6x exponent -1. My new calculator raises the exponent, which is so much nicer. It's just, I just fight like heck to get it to show up on this document camera. So get 6x to the -1 in your calculator. You can graph it if you want. And now my calculator is going to find the area of 6 for me. How do I find areas? Or how do I find definite integrals? I go second, hit the trace calc key, go down to option 7, and my calculator works backwards than by hand. By hand, I do the top number first and the bottom number second. I don't know why the programmers of this calculator do it backwards, but they do. After I hit enter right now, I need to type the 1 in first. So first I'm going to type the 1 and then hit enter. And then I need to type the E. So I hit the second key and the divide key for my E. And then I hit enter. And after I do that, it does everything for me. It shades and shows me the area that it's computing, and it tells me what the area is. On my newer calculator, it's going to write this above. It writes 2 lines. I forget what's on the bottom line, but the 6 you're going to need is on the top line. So if you have a newer calculator like this one, if I try to do it on this one, I just don't think I can make it visible. But if I did y equals 6x, what if I just typed the -1 key? I didn't even get the y key. So y equals, it's just not viewable. It's just worthless. Sorry, it's just not worth my time. Just a lighting issue. All right, so that's that. Let's do another one of these. And it's one that we've already done the integral in section 5.2. You wouldn't remember the integral, but I don't want to spend the time doing the integral. I just want to show you the new part. So in section 5.3, I cut and pasted this, and I figured out that the integral was 1/3 times 5x squared minus 4 to the 6th. And that's really the hard part. That's when we get into the homework. That's where we're going to focus our time. So you wouldn't be able to just look at this and know what that integral is. I did it using, u substitution. And if you wanted to actually do this, on the next 2 pages, you can actually see all the steps to find this integral. We'll do plenty of integrals in the homework, so I didn't want to beat on finding that integral. I just wanted to do the calculus part. So the calculus part, I'm going to take the numbers from the definite integral symbol. After I have the integral that I stole, that I could do by hand, I plug the top number in first. So the top numbers, I plug 1 in. Then I plug the bottom number in second, and I get results. Well, these are ridiculous results to do by hand. I have a calculator that can give me fraction answers if I force it to. So let me do both of these computations on my calculator. First computation. That's just taking that x and plugging in a 1. It's going to be kind of monstrous on this calculator, but I can do it. So, in fact, let me get this first and then multiply it by 1/3. So this part right here, if I go 5 times 1 squared minus 4 up arrow 6, whoa, that comes out to 1. Wasn't expecting that, but that's a good thing. So now I have 1/3 times 1, because I figured out this came out to 1, and now I'm going to multiply by the 1/3, and 1/3 times 1 is just 1/3. So that's one of the 2 computations. Let me do the second computation. Apparently I'm going to get 4096 for the inside of the parentheses. So inside of the parentheses, 5 parentheses 0 squared minus 4 parentheses up arrow 6. That gives me 4096. And now to do this multiplication, I don't need my calculator. This is 1/3 times 4096. And 4096 I can write as 4096 over 1. Multiply 1 times 3 and get 1 times 4096 and get 4096. 3 times 1 and get 3. So these are my results. Now I subtract the results to get the area. So I'm going to go 1/3 minus 4096 over 3. At least I have common denominators. The over 3 part's going to stay, and the numerator is going to be 1 minus 4096, and that gives me negative 4095 over 3. And now I'll divide by 3. So do negative 4095 divided by 3, and I get negative 1365. This means that this graph really exists mostly below, if not entirely below, the x-axis. Negatives indicate portions of the graph below the x-axis, or the majority, if not all, the graph below the x-axis. Let me do this on my calculator to try to match this number up. This might be too much for my calculator. I haven't tried it. So enter this in y1. So y1, clear out anything that's in there. Now I'm entering 20x times 5x squared minus 4 to the 5th power. That looks, for this calculator, the best I could enter that. If I hit graph with my current window, I'm probably not even going to see any of the function because, well, I see a little bit, but it's not particularly interesting. I can't really tell what the graph looks like, but I can still integrate it. Let me do this now. Second, calc, go down to option 7. My calculator wants me to go backwards, so after I hit enter, I do the lower number first, which is 0, and then the upper number second, which is 1. So 0, then enter, 1, and then enter, and I get exactly that minus 1365. My calculator will match up exactly if the answer is not a fraction. If it's a fraction, it'll give me the decimal version. So I think I'm going to pause here, and then we'll start doing the homework. And really, it's just integrating, because plugging the numbers in is not particularly hard if you use your calculator to do some of the grunge. So we'll move into a part 2. The section doesn't have quite as many problems. I think there's 24 problems, so maybe I'll do 8, because there's 12 even and 12 odd.